Now we are going to start the lecture number 40, that is the class for the classical mechanics, that is Livelihoods Theorem for the BS 5th course code PHY 509. Starting with the outline for the Livelihoods Theorem, we are going to discuss first is the proof of the general form of the Livelihoods Theorem, special form of the Livelihoods Theorem. Then we are going to discuss the simple example that realizes the Livelihoods Theorem. Then there are some limitations of the Livelihoods Theorem. The Lorentz transformation, Livelihoods theorem in the extended phase space. There are some applications to the ion beam optics, discussion of the particular cases. Then the Livelihoods theorem for the continuous approximation. To understand the Livelihoods theorem, some are the basic points we have to understand. Livelihoods theorem lies within the space of classical mechanics. It was first formulated by the French mathematician Joseph Lively in 1809 to 1882. It is a conservation law for the Hamiltonian system. These systems constitute a subset of general dynamic systems of point masses or the charges. It means that it discussed the conservation laws for the Hamiltonian systems, and these systems, Hamiltonian systems, constitute a subset of the general dynamical systems of the point masses or the charges are used. The conserved quantity corresponds to a symmetry of Hamiltonian symmetry system, that is the symplectic group, and in the last is applied it applies to the charge particles optics, since we are mostly dealing with the Hamiltonian systems. Now to start with the Livelihoods theorem, given a Hamiltonian system H into Qj Pj T, Qj is the generalized coordinate that J is in subscript, and Pj, that is the conjugate momenta, J is the number of the particle of n degrees of freedom. If we have a Hamiltonian system with the n degrees of freedom, then the volume form for that Hamiltonian system is GV is equal to dq1, dqn, dp1, and so on. dpn is invariant with respect to the canonical transformations. So we say that that volume is invariant, there is no change. So dq1 for the new coordinate system, from old to the new, that dq1 so on dqn, dp1 so on dpn. Canonical transformation from the old coordinate to the new, that is dq1 so on dqn, dp1 and so on dpn. Remember that the canonical transformations are a subset of general transformations of the both generalized coordinates and the Hamiltonian that preserves the form of the canonical equations. We have to keep in remember that the canonical transformations are the subsets of the general transformation of the both generalized coordinates, the Hamiltonian and the Hamiltonian. All are transformable, and that preserve the form of the canonical equations. It means that q1 so on qn p1 to pn Hamiltonian is canonical transformation to the capital Q1 so on capital Q1 P1 capital P1 so on Pn H1, old Hamiltonian to the new Hamiltonian. So for that old coordinate, the Hamiltonian equations are qi is equal to partial h or partial pi, and pi dot qi dot is equal to partial h or partial pi, and pi dot is equal to minus partial h or partial qi. That is the canonical transformation to the new coordinate, that is capital qi dot is equal to partial h prime over partial pi, capital pi dot is equal to minus partial h prime over partial qi. Canonical transformations have the particular property to be defined by the generating functions. All functions of the type f2 is equal to f2 qj pjt define a canonical transformation by means of following transformation rules between old qj pj and new coordinate capital qj pj. So that is written as pi small, that pi is equal to partial f2 qj pjt or partial qi, then capital qi is equal to partial f2 into qj p capital p small qj capital pjt over partial pi. And the new Hamiltonian partial h New Hamiltonian H prime into capital QJ PJ capital PJT is equal to old Hamiltonian capital H QJ PJT plus partial F2 into QJ PJ capital PJT over partial T. As a consequence, we find that metric conditions partial capital Qi or partial Qk is equal to partial square F2 or partial Qk partial capital Pi, and that will be equal to partial Pk or partial capital Pi, provided that partial square F2 or partial Qk partial capital Pi mod is not equal to 0. This relation distinguishes the canonical transformation from the arbitrary coordinate transformation arbitrary coordinate transformation where the above relation does not hold. We are now ready to prove the Livelihoods theorem. For arbitrary coordinate transformations, the mapping of the volume form dV is determined by the determinant capital D of the Jacobi matrix, that is dq1 so on dq1 dp1 so on dpn is equal to capital D dq1 small dq1 so on dq small dqn dpi small dpn with capital D is equal to that is for the Jacobian determinant capital D is equal to partial into q1 so on q1 comma capital P1 to so on P capital Pn divided by partial uh, q1 so on qn small comma pi so and small pn. The proof of Livelihoods theorem thus means to show that the Jacobi determinant matrix and capital D is equal to 1. For simplicity, we prove Livelihoods theorem for the case of a system of 1 degree of freedom, that is n is equal to 1. For coordinate transformation, capital Q is equal to capital Q into coordinate QP variable QP small and capital P is equal to capital P variable small q small p. The determinant capital D is given by capital D is equal to partial capital QP over partial small qp is equal to partial capital Q or partial Q or into partial capital P or partial P minus partial capital Q over partial P partial capital P or partial small q. According to the theorem of the partial derivatives of the inverse mapping, q is equal to q into capital QP, small p is equal to p into capital QP. We have partial small p or partial capital P is equal to 1 over d into partial capital Q or partial small q. So that capital D can be expressed as capital D is equal to partial capital Q over small q into partial uh, small p over partial capital P. We have cross multiplied and written it with the minus 1 power. If the particular transformation is canonical, then a generating function f2 into small q capital pt p comma d exists. The transformation rules then follow from f2 q capital pt as capital Q is equal to partial f2 or partial capital P and small p is equal to partial f2 or partial small q. Inserting capital Q and small p into the equation for capital D, we find that capital D is equal to partial capital Q partial small q into partial small p over partial capital Q mod of minus 1, and that gives the by inserting the values, that is partial square f2 or partial small q partial capital P into partial square f2 or partial capital P into partial small q whole power minus 1, and by solving that gives that is equal to 1. As by definition of f2 we are allowed to interchange the sequence of the partial derivatives, so a proof of general case of a system of n degrees of freedom is worked out similarly that we got the answer for the capital D, that is equal to 1. If the coordinate transformation is defined in a mixed form of old and new coordinates by capital Qi is equal to capital Qi into Q small qj pj and P small pi is equal to small pi into capital Qj pj capital Pj, then the determinant of the Jacobi has the general representation as capital D is equal to partial into capital Q1 to Qn divided by partial into small q1 to small qn into partial small p1 to pn divided by partial capital P1 to capital Pn. whole power minus 1, which generalizes the case n is equal to 1. If the transformation rules can be derived from a generating function f2 into small qj pj, small qj into capital Pj, comma d, then the transformation is canonical. As above, inserting capital Q1 is equal capital Qi is equal to partial f2 or partial capital Pi, and small pi is equal to partial f2 over partial small qi yields capital D is equal to determinant partial square f2 or partial qj small into partial capital Pi into mod of partial square f2 or partial capital Pj into partial small qj whole power minus 1, and that gives the value is equal to 1. Since the equation 1, the since the first number 1, the sequence of the partial derivatives can be interchanged first thing, so that can be cross multiplied and cancelled. The transpose matrices have the same determinant as shown in that means that the transpose of the same mod gives the value of 1. Now to solve the special form of Livelihoods theorem, we easily verify that the canonical transformation generated by f2 into small qj capital Pj t is equal to summation I is equal to 1 to n q small qi capital Pi plus capital H into small qj Pj t del t uh, curly del t pushes a Hamiltonian system one step curly del t forward in time, that is capital Pi is equal to small pi plus pi dot del t, capital Qi is equal to small qi plus qi dot into del t, and capital H prime is equal to capital H plus H dot del t. As we can apply the transformation an arbitrary number of times in sequence, the mapping over the finite time steps in the also the canonical. Hence, the time evolution of a Hamiltonian system capital H Qj Pj itself constitutes a canonical transformation. If the Hamiltonian system gives an evolution in time, so itself Hamiltonian is also a canonical transformation. We may thus formulate the special version of Livelihoods theorem as given a Hamiltonian system capital H Q J P J T of n degrees of freedom, then the volume form dV is equal to dq1, dqn, dp1, so on, dpn is invariant in the course of the system's time evolution. So V is equal to integral V to so on, integral dq1, so on, dq1, dp1, so on, dpn is constant, is equal to constant. Interpretation: as the system moves forward in time, the system point q1 to qn, p1 to pn changes its location in the 2n-dimensional top phase space. A small but finite volume V around its point remains invariant. The local point density around the system point in the top phase space remains invariant. Note that a system of capital N interacting point charges in 3D space represent one point in 6n-dimensional top phase space. Number 2, a set of such points represents an ensemble of the system which of course do not interact. Number 3, an ensemble of a system is given by a set of physical systems that follow the same equations of motion while having the different initial conditions. Number 4, to illustrate the Livelihoods theorem graphically to show that the local point density remains unchanged, we discuss an ensemble 1 degree of freedom of this system. In that case, top phase space has the dimension 2, hence that can be realized. Now we have an example. As an example, we consider mathematical pendulum with the Hamiltonian capital H small q p is equal to 1 over 2 p square plus omega square into 1 cos q and omega square is equal to g by L. From the canonical equations, the equation of motion follows q double dot plus omega square sine q is equal to 0. We plot the time evolution of set of top phase space points of the each of them having particular initial conditions. In the first case, the initial distributions of the point is uniform, whereas in the second sequence, the initial distribution is Gaussian. Here you can see the pictorial diagram for the evolution for the uniform canonical transformation, and the above is the uniform evolution of the time, and in the bottom is a Gaussian evolution top phase space distribution for the mathematical pendulum. There are some limitations. We consider two Cartesian frames of reference xyz and x prime yz that moves with the speed to each other in x direction at constant velocity c beta, such that at gamma is equal to 1 under root 1 divided by under root 1 minus beta is greater than equal to 1. The mapping is considered by the Lorentz transformation, so that is given as x prime ct prime is equal to matrix gamma in gamma minus beta gamma, or minus beta gamma into gamma is into x over ct, and px prime over px prime and e pi prime over c is equal to gamma minus beta gamma over minus beta gamma into gamma, and column is px over e over c. As this transformation also maps the time, it does not constitute a conventional canonical transformation as used above. It can be formulated as a generalized canonical transformation in the extended phase space. Uh, if we calculate the mapping factor capital D of the volume formed dx dpx under Lorentz transformation, we find that capital D is equal to partial x prime px prime over partial x px is equal to matrix mod of partial x over partial x prime over partial x prime over partial px prime over partial px prime over partial px is equal to mod of gamma 0 0 gamma, and that gives gamma square is not equal to 1. The Livelihoods theorem does not hold for transformations between the beam and the laboratory system. For this case, we can must resort to the extended phase space version of Livelihoods theorem and investigate the mapping of the extended volume form dVE is equal to dx dp dte. The determinant capital DE of the corresponding Jacobi matrix is then capital D is equal to partial x prime px prime d t prime e prime over partial in x px t e, that is equal to 1. Under the Lorentz transformation, only the extended phase space version of the Livelihoods theorem is applicable. Now the discussion. General case of charge particle beam optics, system of capital N interacting point charges in the three-dimensional ds space. One point in number one point is in the six-dimensional top phase space. Number two, an ensemble of such system forms the point distribution top phase space. Number three, the local point density in top phase space is conserved. Number four, not particularly useful for our purposes. Now the question arises that what happens if the particle interaction forces are so weak that they can be neglected, or you can say zero space charge limit. Each of the n particle moves in its own six-dimensional mu phase space. The six-dimensional top phase space factorizes into n copies of the six-dimensional mu phase space. Number 3, Livelihoods theorem holds separately for each particle in the mu phase space. Number 4, the set of capital N particles form a point of distribution in the mu phase space with the local point density being conserved, uh, such that mu phase space Livelihoods theorem. Here is another question: what happens if the particle interaction forces are no longer weaker? Number 1, then the local point density in the six-dimensional mu phase space is no longer conserved. The mu phase space Livelihoods theorem does not hold anymore, and number 2, we are thrown back to the not very helpful top phase space Livelihoods theorem. Number 3, yet there is one particular approximation that leads us out of this dilemma. There is another question, number 4. Does a special case exist where local point density in the mu phase space is conserved while the interaction forces are not negligible? Yes, if we can approximate the particle interaction forces by smooth field that is equivalent to an externally applied field continuous approximation. Number 2, Poisson's solved method. Poisson solved method. Number 1, we pretend that we pretend that the particles do not mutually interact. Number 2, instead we calculate the smoothed global field generated by all particles and let the field act back on all particles just if it were an external field. The mu phase space Livelihoods theorem hold. Number 2, binary interparticle forces are eliminated. Continuous approximation. The distribution of interacting particles in mu phase space is approximated by a continuous mu phase space probability density function of x, y, z, px, py, pz, and t. Now the connection to the particle picture, the product f of x y z p x p y p z t and del x del y del z del p x del py del p z yields the probability of finding a particle inside a small volume del x del y del z del p x del py del p z around a mu phase space at a point x y z p x p y p z at the time t. F is by definition a continuous function of the mu phase space. F does not provide any information on the individual particles, but it gives the information on the system of the particles or number of particles. We assume that no particles get lost. In the continuous picture, it means that the integral over the probability density remains constant. Integral, so on integral f of x, y, z, p, x, p, y, p, z, t into dx, dy, dz, dpx, dpy, dpz is equivalent to 1. In differential form, this is equivalent to the continuity equation partial f over partial t plus divergence of j, that is equal to 0. J is equal to f dot into x dot y dot z dot px dot py dot and pz dot, the mu phase space probability current density. In explicit form, the continuity equation writes partial f over partial t plus partial f over partial x into f x dot plus partial over partial px into f px dot plus so on is equal to 0. Special case, a continuous Hamiltonian h into x y z px py pzt exists on so that the motion of the mu phase space points is described by canonical equations. X dot is equal to partial x over partial px partial px px dot is equal to minus partial h over partial x. We insert the canonical equation in the continuity equation, that is partial f over partial t plus partial over partial x into f into partial h over partial px minus partial over partial px into f partial h over partial x plus so on, that is equal to 0. Applying the product rule, we find partial f over partial t plus partial f over partial x partial h over partial px plus f partial square h over partial x partial px minus partial f over partial px partial h over partial px partial x minus f of f into partial square h over partial px partial x plus so on is equal to 0. Mm, uh, sorry There is partial f over partial t plus partial f over partial x partial h over partial px plus f into partial square h over partial px partial px minus partial f over partial x partial h over partial x minus f into partial square h over partial px square partial x plus minus so on, that is equal to 0. The term containing the second derivatives of h are cancelled, so partial f over partial t plus partial f over partial x partial h over partial px minus partial f over partial px partial h over partial x plus so on, that is equal to 0. Inserting back the canonical equations, we have finally got partial f over partial t plus partial f over partial x dx over dt plus partial f over partial px dpx over dt plus so on equivalent for df over dt, that is equal to 0. If we follow the time evolution of a mu phase space point x t y of t z of t px of t py of t pz of t, we observe that the probability density f at the point remains constant. Now we summarize the topic. The local point density in the sixth dimension mu phase space remains invariant if we approximate the actual interaction field by a continuous field that corresponds to a thought continuous charge distribution. Final remark is the local point density is within the projection into the two-dimensional dimensional emittance phase planes x px y px y x del z del pz are of course not conserved in general, even if the local density is conserved in the six-dimensional mu phase space. Example: the time in evolution of a x prime phase plane distribution under the space chart distributions. Here you can see the uh, graphical representation. The time evolution of x prime phase plane projections of an unbunched charged particles beam in a beam transport channel. The local point density and hence the area of the populated region in these projection is only conserved if number one, the system's Hamiltonian can be split into h is equal to hx plus hy plus hz. Number two, the actual particle interaction field is approximated by the smoothed field. Only then the mu phase space Livelihoods theorem hold separately in each phase space. Now the sole example is of KV beam. theoretically helpful but not very realistic beam model. These are the references you can follow for the topic to understand the Goldstein and the analytical mechanics, classical dynamics of the particles, and the classical mechanics by John R. Taylor. These are the books you can follow for the purpose of your understanding of the course. Hopefully the topic was understandable. If there is any kind of difficulty, you can ask in the class. Thank you so much. Allah Hafiz.